Hi everyone, my name is Cheng. I work as a research technician at CanmetMATERIALS, Natural Resources Canada. Today, I would like to share some results on our recent study on the constraint effect on fracture toughness resistance of an X60 pipe steel. Our paper number is 193. This study consists of experimental tests, which was conducted previously by my colleague Liang, and the material was provided by Professor Stijn at Ghent University in Belgium, which is greatly appreciated. Dr. Yifan Huang at Candu Energy provided huge support on the finite element analysis. Dr. Jidong Kang and Gianetto are the team leaders and have given great advice on this project. Thank you everyone for your great contribution. My presentation will include, firstly, the introduction and objective of current study, next, experimental and finite element analysis, and finally, results and discussion, as well as conclusions and future work. R curves, including J and CDOD R curves, have been widely used in the integrity assessment and strain-based design of energy pipelines. Fracture specimens with different geometric configurations and subjected to different types of loading lead to different R curves, which is the so-called constraint effect. The figure below shows some typical R curves obtained from fracture toughness tests. The shallow cracked SET specimen leads to the highest, while the deeply cracked CT specimen leads to the lowest. The shallow cracked SEB results in a higher R curve than that from the deeply cracked SEB specimen. Constraint parameter is a quantitative characterization of the crack tip constraint state. Existing constraint parameters include the stress-based ones, such as Q, A2, H, and TZ, and the plastic strain-based ones, such as CP, AP, and VP. Our current study aims to evaluate the adequacy of existing constraint parameters in terms of correlating the toughness of an X60 pipe steel to constraint level for currently tested specimens. And in order to do this, we firstly conducted fracture toughness testing on SEB and SET specimens with different initial crack lengths, and then performed finite element analysis to obtain the 11 constraint parameters, and finally correlated the constraint parameters to measured fracture toughness data. Tensile tests of two rectangular tensile specimens machined in piped longitudinal direction were tested at room temperature. The black lines are the engineering stress strain curves, and the blue lines are the true stress strain curves. The red line is the average fit line in the form of a Ramberg-Osgood relation, and the equation is given as well. The fracture test specimens are longitudinally oriented and were notched in through thickness direction. The nominal initial crack size to width ratios were 0.25 and 0.50. The specimen's width and thickness were both 12 millimeters and side grooved by 15% of the thickness to maintain a straight crack front during propagation. The JR curve testing used ASTM E1820 and CanmetMATERIALS procedures for the SEB and SET specimens respectively, and a 3-clip gauge were attached to the specimen to calculate the J-converted CDOD and geometric CDOD values by the XMobile method. This figure here shows the knife edge fixture. The commercial software Abacus was used for finite element analysis. Only a quarter of the specimen were modeled due to symmetry. A blunt crack tip with a radius of 0.05 millimeter was modeled to simulate the electrical discharge machining process, as well as to facilitate the finite strain analysis. A sharp V-notch with 45 degrees was adopted to simulate the side groove. The elastic plastic model based on the J2 incremental theory of plasticity and isotropic hardening was assigned to the material. The model had a number of nose end elements of 50,000 and 45,000 approximately. The in-plane and out-of-plane mesh density convergence was also checked, and the J value were calculated using the crack the virtual crack extension method and averaged in the thickness direction. And this figure shows a shallow cracked SET model and a deeply cracked SEB model, and also the detailed mesh around the crack tip. In our study, 11 constraint parameters were calculated and evaluated, and here we only show 4 of them. The Q parameter can quantify the difference between the actual and reference stress fields ahead of the crack tip, as shown in this equation. And it is calculated at a normalized distance of 2 at the midplane. The H parameter is called stress triaxiality and is defined as the ratio of hydrostatic stress to vormesis stress. The CP parameter is the equivalent plastic radius and was proposed to be a good unified measure of both in-plane and out-of-plane constraints. It is proportional to the square root of plastic work APL by the external load, which is shown in the left figure, over the specimen thickness. The right figure shows the geometric definition of CP. The AP parameter is defined on the basis of the area surrounded by the equivalent plastic strain isoline ahead of the crack tip of the tested specimen and the reference specimen. And this figure shows the equivalent plastic strain contours with the yellow color surrounded by the red dotted line being the 0.2 isoline. In our study, 0.2 isoline of the deeply cracked SEB specimen was chosen as the reference area. And now we are showing the tested JR curves and CDODR curves. In general, we could see the expected trends of higher resistance curves for both shallow notched specimen types and tension versus bending loading mode. And also, the shallow cracked SEB specimen exhibit resistance curves similar to the deeply notched SET specimen. Note that the average curve was fitted and also shown in this figure. From the CDODR curves, the CDOD obtained from the J conversion method is consistently lower than the CDOD obtained from the double clip gauge X mobile method, which is consistent with previous CDOD studies. And now we're showing the variation of different constraint parameters with normalized J values. The left figure shows the constraint parameter QHRR is much lower for the shallow cracks than for deep cracks in both SEB and SET specimens. And also, the shallow cracked SEB specimens exhibit a constraint condition similar to the intrinsically low constraint deeply notched SET specimen when the loading level is within 0.075. For SEB specimens, the increasingly decreasing value of Q after a certain loading level indicate the significant influence of the global bending stress on the crack tip stress fields, and especially for the deeply cracked specimens. Similarly, for the H parameter, deeply cracked SEB specimens have the highest constraint level and shallow cracked SET specimen has the lowest. The constraint level of shallow cracked SEB and deeply cracked SET are similar. Same trends can be observed for CP and AP parameters as well. This table summarizes all the calculated constraint parameters for all the specimens considered. Now we are showing the variation of constraint parameters and J or CDOD values. The critical J values are plotted on the left vertical bar, and the critical CDOD values calculated from the J conversion and X mobile methods are plotted on the right vertical bar. The horizontal bar is the value of the constraint parameters. In this slide, left figure shows a QHRR and right figure shows H. And in the next slide, left figure shows CP and right figure shows AP. We can see that in general, all the constraint parameters are able to construct a master curve and correlate with J and CDOD values. And from above, AP was found to have the most promising trend in terms of correlating the material's toughness to constraint level for currently tested specimens. Generally has a coefficient of determination R squared value greater than 0.9, except for critical J converted CTOD, R square value being about 0.75. In terms of the stress-based constraint parameters, QHRR, QSSY, and H have more promising trends compared to others. In summary, AP works the best. Here come our conclusions. Fracture toughness test results show that higher R curves for both shallow versus deeply notched specimen types and tension versus bending loading mode. The shallow cracked SEB specimens exhibit a constraint condition similar to the intrinsically low constraint deeply notched SET specimen. The CTOD obtained from J conversion method is consistently lower than the CTOD tested from the double clip gauge X mobile method, which is consistent with previous CTOD studies. AP parameter based on the normalized equivalent plastic strain contour was found to have the most promising trend in terms of correlating the material's toughness to constraint level for currently tested specimens. And note that the lack of large number of tests is one of the limitations in current study. Further ongoing investigations are underway to extend this evaluation to X100, X80, and X70 pipe steels to allow for the characterization of strain hardening effect. And the welding effect in weldment and heat affected zone will also be evaluated. Thank you very much.